Hello, everybody. Thank you so much for joining me tonight. Today, we're going to be talking about, we're going to have chapter 4, 5, and 6. And let's start with chapter 4. This is going to be about gates and circuits. As you may have probably heard in the past, gates are basically a number of transistors put together that allows a certain mathematical equation to happen. For example, addition, multiplication, or something like that. And it basically allows you to have certain number of inputs and a certain number of outputs. And that's basically what a gate is. And then from a number of gates, you can actually end up with a circuit. For example, let's just we'll get to that, and I will talk extensively about that. So the goal from this chapter is to identify the basic gates, describe the behavior of each, and we're going to see the AND, OR, XOR, NOT. So you'll understand them. And of course, we're going to probably talk, not probably, we're going to talk about the nomenclatures. We're going to talk about uh, the way we write the symbols and the operators and things like that. And you may see different types of writing, and I'm going to go into that too. This book has a very specific type of writing when they say and or NAND or anything like that. But I'll give you a little bit of pointers of what you may have or may see in other books and in other, probably even other languages. So we're going to describe how gates are implemented using transistors. We're going to combine basic gates into circuits and describe the behavior of gates and circuits using Boolean expressions, truth tables, and logic diagrams. We will go a little bit uh, more into just the logic diagrams. I will show you some things that you can do some research and know a little bit more about them that will help you if you want to get into this science and you want to actually build circuits using just gates. Of course, nowadays people don't use gates unless if you want to just play with that. We use microprocessors, okay? And that's a lot better solution than just gates. So chapter's goal, we're going to compare contrast half adder and full adder. Basically, you're going to see the difference between a half adder and a full adder. An adder is just like what it means, add, but it's half. When you say half, meaning it simply does not use the carry. Okay, so remember how when you do carry calculation between addition, for example, between two numbers, and there is a carry that goes to the next strand and so on. The half adder does not consider the carry. Full adder does. That's the only difference, and we're going to see what it means later. Describe how a multiplexer works. A multiplexer is just something that brings in multiple inputs and creates an output. Not only that, it has multiple inputs, and with a certain trigger, it gives us one of the inputs in the output. For example, we'll go over in a second, so we will get to it. Gates. So it's a device that performs basic operation in electrical signals. Circuits, it's gates combined to perform more complicated tasks. Uh, so think of it like if a gate is like a provides plus sign, a circuit is something that provides combination of plus of some x, y multiplied by z, all that divided by a y, let's say t, right? So these are four inputs. So four inputs, they will become in a certain combination of circuitry. We're gonna make it all whatever inside, and then there will be an output, right? That is a circuit. This is an output. These are inputs. Okay, that's a circuit. A gate is one. And there's multiple. There are multiple displays depending on what type of gate it is. So we'll have an A, for example, and a B, and there will be an output of a C. We don't always talk about this part, but you need to always remember that every circuit has two elements. One is called the ground, GND. You're going to see it explained in different ways. Maybe sometimes you're going to see a zero, the ground, uh, or written, actually spelled out ground. Okay, this is a voltage. It's called. Sometimes you're going to see it VCC, voltage continuous current. Generally, it's a 5 volts. Or sometimes you're not going to see the VCC. You're just going to see 5 volt and 0 here. So that's what it means. So you feed the circuit a certain energy, and then this circuit does something. With these two inputs, it creates an output. Okay. Some circuits use more than just the voltage and the ground. Some of them use also what we call a clock, CLK. A clock is a tick. He basically says, okay, I want you to act like this after every 10 ticks, for example. When clock keeps going tick tock, tick tock, tick tock, it will get to that point where it triggers here, and then this is where these two will give us some output. This is just a little bit going a little bit above and explaining what we're talking about. Okay, it is not complicated, so you don't get too confused. This is something that is just because you probably never heard of it doesn't mean that you're not going to be able to understand it. It's very simple concepts. You're not going to do anything math or anything like that in this class. All you need is to understand the concepts. There will be some small exercises, but I'll explain enough in these lectures that you wouldn't have to have any problems with them. So computers and electricity, Boolean expressions. That's when you hear like false, true. That's Boolean, okay? Logic diagrams, you're going to see logics. You're going to see truth tables. So the Boolean expressions, it's use of Boolean algebra, mathematical notation for expressing two-value logic, okay? So this is an expression. How do we write the, the thing, okay? The logic diagrams, that's how, so this, for example, will be if we're using the operator plus, A plus B, this is actually also called OR. So this is a Boolean expression. This expression right here is a Boolean expression, okay? But if we want to use this in a logical diagram, we're going to do it like this. It's pointy, okay? It's actually not really like that. Let's see. So two inputs, right? And this thing is like this. Here's an up, A, B, and this is A plus B. Or sometimes you're going to see it A or B, okay? Either plus or is both explaining. It's the right thing, same thing. The truth table is how do we represent the ones and the zeros whenever we have something like this. The way we're going to write it is we're going to say B, A, B, then we're going to put A plus B in here. It's going to be a table like this. Then we're going to see A and B. If you have two, how many combinations would you have? It's either 0, 0 or 0, 1 or 1, 0 or 1, 1. These are the only combinations. That's the good thing about binary because you don't have a lot of options. Okay, the numbers you have are either 0 or 1. You don't have all the way to 9 or to millions like we have in decimal. Here, of course, you can represent millions in zeros and ones as well, but I'm just saying the combination between A and B. What are the possible combinations between these two? So if it is 0 and 0 because it's a plus, generally it says that either one. If they are both 0, it is 0. Otherwise, it's a 1. That's what A plus B means. So this is a truth table. This is how I represent truth table. This is how I represent a logic diagram, and this is how I represent the Boolean expression. Okay, just so you can see it in action better than just give you an a definition by words, because this is much better to see it and what it means than just read it. Okay, now we're going to go a little bit faster because we cannot sit much. I don't want you to be overwhelmed because you have 3 chapters this week. So the types of gates we know there are in generally just six. Okay, with these six you can do crazy things. So not, you give an input and it inverts it. Okay, whatever input you give it inverts it. We're gonna go through this so you don't have to spend too much on it later. So not, if you give it a zero, it's gonna give you a one. If you give it a one, it's gonna give you a zero. How it's represented? Just like this. That's not. Okay, as an input, gives you a output. And it's like multiplication. So it's the way it's represented here, by the way, the like what's represented for not, if it's a, the way in the book it's represented a prime. Okay. But in other books, it's going to be represented with a bar. Okay. That's one of the representations. Let me think. In other representations, it's going to be represented like with this symbol. This symbol here means opposite of this number. Okay, let's see like this. Dependent. So generally, you're going to see, internationally, you're going to see this sign. But in our book, it is represented like this. So A prime means the opposite of A. Just remember that. And A prime, so if you get A here, this is actually A prime. And it's represented with the dots. So A dot B. It's just like multiplication. A, B. Okay. You'll see it in different ways. Or sometimes you're just going to say A and B. Never A and B. Remember that. This representation does not exist in Boolean. Don't use that. Even this one is never used. We use this one specifically. Dots. What it means is you're having two numbers, two inputs, and just like and, this is the representation how it looks like. So this is AB, and this is A dot B. If there is a zero, the output is zero. Remember, zero multiplied by anything is a zero. So if there is a zero, either A or B, the output is zero. Otherwise, it's a one. That means that only when A and B are ones, only when A equal one, B equal one, that's AB equal one. Otherwise, it's a zero. Okay, or is a plus. Okay, if there is a one in between, it's going to be one. Otherwise, it's zeros. Okay, XOR is the sign. What XOR means, either if they are the same. XOR is used to compare. So if they are the same, if A and B are the same, it gives you zero. If they are not the same, it gives you one. We're going to get to that and see if I'm mistaken here. So it compares A and B. It gives you a result if they are the same. It gives you another result if they are not the same. So you can imagine the XOR, the value of XOR in programming at least, because you can actually turn a program or a certain calculation into, if it has a loop, it has conditions and all that, you can turn it into something you can represent with gates. That means you can do more than just doing calculations. You can compare and draw results and use that and bring it back as a loop. The same thing you do for programming, you can use with gates, but we're talking a little bit ahead here. NAND is the opposite, is the prime of AND. So with this N here, that's what it means. So it's A times B opposite. That's NAND. NOR is the opposite of OR. So it's I plus B. Oh. And we're going to talk about some rules later on, because there is ways to actually remove these parentheses if you have opposite like this. Okay. Oh. And do. Okay. Let's go further. 7. So we talked about that. We talked about that. We talked about that. See how we are going. Okay, we talked about source. So if they are the same, it's a 0. Otherwise, it's a 1. See? So if they are the same, if A and B are the same, it's a 0. See, 1, 1 is a 0. Otherwise, it's a 1. So it's comparing them. It's comparing A and B, and it's looking, it gives you 1 when they are different. That's basically what it is. XOR, we talked about it. This is NAND. This is NOR gates. And this is simply 3 inputs. Same exact rules apply. Transistors, this is the part where we need to talk a little bit, and we're going to go, just follow the PowerPoint. So what is a transistor? A transistor is basically a device that only gives you an output when it's excited to a certain level of voltage. Let's explain it a little bit. And you see here, it's a collector, a base, and emitter. This is the emitter, this is the base, this is the collector, or the source. So we'll have a voltage here. For example, let's say we're going to have a 5 volt here. We're going to have 5 volts here, right? This is a 0. It's almost like an interrupter. See how you know how in electronics you have an interrupter like this? Once it connects, it passes the electricity through. That's the same thing. The only difference is this guy right here, it does not connect unless if it's triggered. See, it looks like this. It's triggered through the base with a certain voltage. That's the only time when it connects these two. If you have a VCC here, which is 5 volts, you have 0. If this is not connected, there is no connection here. So the 5 volt does not connect to the 0. There is no connection. What you want is when you have, so it's either the base will either connect to the 0 or connect this thing here. If it connects the source to 0, you're going to end up with a 0 volt here. That means you get a 0 as an output. If, let's not confuse you too much. Let's do it again. Okay. Normally we have 5 volts here in the source, right? And we have a 0 here. If this guy is passing electricity, this 0 becomes here because it's connected. This is the output, 0 volt. With 0 volt, it means this output is 0. So generally, this is always 0. I mean, this is always 1. Only when this guy connects, it becomes 0. So that's basically what it is. Okay. So the base, and you may ask, oh, what kind of voltage I'm going to get into the base? Depending on what type of technology this transistor is, it's either built with CMOS. There's different types, CMOS, TTL. You can find the abbreviations, and they're both excited with a certain number of voltages. So CMOS, the voltage is, I think, 3.5, and TTL is 5 volts. So 3.5 is considered 1, and 5 volt for TTL is considered 1. That tells you if you are using both technologies in the same circuit, that's going to cause you some trouble. So there is some ways that actually you can combine both by using inverters and things like that. But there's ways to fix this problem. Anyway, generally, the base is in a range of 0.7 volts. You're not going to see this in this book, but generally, it's actually a low voltage that excites the base, and that's all this transistor needs. It needs just a little bit of voltage. It excites it, and it connects this thing. And then, of course, the rest happens. Okay, let's go further. And you can tell by having this capability, you can have this output as an input in another transistor, right? If you have 5 volts here, and another transistor is somewhere around here, for example, You only need 0.7 volts to be excited. 5 volt is enough to excite this transistor, the next one, for example. And it will pass through too. So you can use a combination of transistors and you can create miracles. And that's exactly what happened in science today. Because instead of having talking about only two transistors, now we're talking about billions of them. Okay, very microscopic implementations. So what's the outputs? If the base signal is low, the transistor acts like an open switch. We already explained all that. Now, let's see different things. See how the representation now is with transistors for different type of gates. Don't get too confused. Don't get too intimidated. It's very simple. Look at it, okay? 5 volts here, and this is the ground. This is a NOT gate. That means whatever you have in the N, it's the opposite that you have here, okay? If this is excited, that means this is 0. So this is a NOT gate. It's the opposite. It gives you a 0 always, only when this guy, I mean, only when it's not excited, it gives you a 1. Okay? So if the base is not excited, it's a 1 because that's the source. It goes through. The moment you excite the base, this guy passes through, and then you're going to get a 0. So it's a NOT gate. Remember that. A transistor on its own is a NOT gate. NAND gates. The source. So this is an opposite of an AND. Why? Because this line right here will not be passing any voltage only when both of them are connected. They're both connecting. That's the only time where it's going to act with using both as an AND. Okay, it's an AND, but because transistors work as the inverters, then it's an AND. Same way for a NOR. You can imagine after this input output, if you want to switch this to a different type of gate, you can use an inverter. You can use another transistor and it will invert the whole thing. And you're going to see that's basically what happens in real life. Now, NOR, or that's either one, if either one of these is connected, then it's the whole thing is connected, right? Either one of them. Didn't have to be two. And of course, they have to be two. This one is not. Combination circuit and sequential circuit. We'll explain them really quick. In combination, combining multiple gates into one. Sequential circuit, you add in time. Okay. Now we're going to add some type of time consideration. So the input function, input value, the existing state of the circuit. Existing state. That means that state can change. Now we're including time into the equation. Okay, that's why we call it sequential circuit. For example, you're going to tell it, I want you to do this calculation, but not right now. In the next cycle, do this calculation. And the following cycle, do the other calculation, so on. So that's sequential logic. So this is which is the Boolean expression for A, B plus C is A, B, and C. So all we did is, this is an AND, see? This is an AND, that's multiplication. AC is another multiplication, so A with B and then A with C. Two gates, so this is two gates, right? It's gate 1, gate 2, gate 1, gate 2, and then both of them we use the plus, became a smiley face. So A and B is this guy. A and C is this guy. And this plus right here is this guy. Okay? So that's basically it. So you don't get too intimidated. It's simple, it's just a representation. This here is the truth table. Okay? For example, B plus C, you just go through the whole thing and do the math, okay? 0, 0, it will be a 0, 0, 1, it will be a 1. And you may ask, oh, what are the rules for addition for the zeros and ones? We talked about that in the past. Generally, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 1. Carry 1. This carry will cause some problems later in your understanding of the combinational logic. And we talk about it in full adders and things like that. So for the moment, just remember that the carry is not considered if you're doing 1 plus 1. For example, look at this calculation right here. 1, B and C, right? 1 plus 1 is 1. But nobody's caring about the carry. But there is a carry somewhere, okay? Sitting somewhere, waiting to be used somehow. And we do use those. So there's a little bit of logic into that, but it's not the scope of this class. Someday we'll talk about it and see how the carry can cause havoc. Anyway, so consider the following Boolean expression: A multiplied or times B plus C. So B plus C, that's this guy right here, and then you multiplied it, and that's the end. This is or just remember it. Every time you see it pointy, that's a plus. Pointy one right here, that's a plus. Completely round, that's multiplication. But we don't use the X, we use actually a dot. Okay? Just so you know the difference. There is different ways. We never talked about it here, but imagine if I give you a truth table. I didn't give you this first. I didn't say this first. I just gave you a truth table like this. There is a way to convert from a truth table, even without giving you B plus C. Let's just say this B plus C is a Y. It's like, hey, the out or just or output. It's going to be the question will be, we have a circuit that have 3 inputs and 1 output. The inputs are A, B, C. Doesn't have to be. They don't have to tell you what type, to name them anyway. 3 inputs and the output. And this is the truth table for this equation, okay, or this circuit. Go ahead and build me this circuit. If that's the question, there is some ways of doing it. Do research about Carnot tables. Carnot tables. Carnot. Karnaught, if I'm not mistaken. Carnot tables. What it does basically, you actually represent the truth table in a different way, and you're gonna use some. Let me see. We're not gonna go through it, but I'm just gonna give you an example. Okay, you basically put some. Let's say you put AB here, and you put C and BC, for example. And you're going to fill it up with the zeros and ones. And there is a way to select the zeros and ones and create a certain calculation. This is too much talking about the Carnot table, but it is extremely helpful because by switching this to Carnot table, I think that's how it's written. Carnot, this is an R. Okay, maybe I wrote it wrong, but you can figure it out. So by representing this into a Carnot table, you can figure out the gates and how they're going to be lining up and all that good stuff. So this is, it's not hard neither, because the rules for the Carnot table are very simple. You just have to do them right. And you can actually represent from this, you can get to this. Now, this is another combination circuit. We're not going to go and explain each one of them and how they're represented. It's simply something you have to go over and read yourself. So these are rules, okay? These are the properties of Boolean algebra. You may ask, well, why? Because sometimes you get, let's say you get a question and you have to simplify it. Because the biggest thing you don't want too many gates. Because more gates mean more calculations. More calculations mean longer time, more energy. So if you want to reduce a certain expression, you have to know these rules so you can reduce it. The most important one they're all important, of course, is the De Morgan law. De Morgan's law is basically switches between the OR and the AND if you have an inverter. A and B inverted, which is prime, is equal to A prime, or, see, we went from AND to or b prime. The other way is also true. A plus b, which is a or b prime, is actually equal to a prime. So we distributed the prime on the number. See, this prime was outside the parentheses. Now it's prime for the a and prime for the b. So inverter of a, inverter of b. So the inverter of a plus b is actually inverting a multiplied by the inverting b. So the De Morgan allows you to get rid of the parentheses if you have a whole bunch of them. So see how it's no longer parentheses. The adders, we talked a little bit about it. And this is adder. See how you have the sum A, B, and there is a carry. And the carry only exists when A and B are both ones. Talked about that. Circuit diagram representing half adder. You can remember it, right? So this is a XOR gate. We didn't see it, but this is XOR. Remember, it's just looking as a comparison between A and B. I always make that mistake. A and B, and this is A and B. If they are the same, it's a 0. If they are the same, it's a 0. Sometimes you have to look. So this is a full adder. So it's actually considering the carry. So the carry in from a previous calculation. And then you're doing the using it to provide a sum and another carry out. Here's the carry out. You don't need to understand the whole thing, but feel free if you want to. Generally, if you look at it, if you do the addition, you'll see. But this is an AND, this is an AND, this is a plus, and this is a XOR. Okay. Multiplexer. What's a multiplexer? It's a circuit that uses few inputs and then ultimately will give you one of them at the output based on some kind of a trigger that you do for it. So, for example, here is some kind of multiplexer. Okay, it will have inputs, and because of some kind of trigger, it's going to give you certain outputs. Let's say this is A, B. I'm going to explain it really quick and you understand, so you don't have to really think about it again ever. Call this control. You're going to see them again if you study a little bit more computer science. Control bits are something that you're always going to see. So there's some control bits that come. Let's say this multiplexer, the control bits, remember this is 5 digits, right? And let's say it's gonna, the control bits will come up with like this, 0001. The control bit is coming up like the 0001. If it comes like this, it automatically, for example, just giving the example, it basically says control these gates. There's gates inside here. Only use the last one, 0001. Only pass me the last one. And the last one is what's going to be passing through. Whatever is in E, 0 or 1, will be coming out the outputs. This is what a multiplexer does. You can say, give me the second gate, for example, 010000. Meaning it's this guy that's going to be passing through. Okay, it's not exactly like this. The point is, based on some control bits, one of the inputs will be passing through. Okay, why is it used? Multiplexers are extremely important in transferring data through long distances. You may ask why? Because we can transfer in serial one digit after the other, and we can tell the code, this is the first one, this is the second one, this is the third one. Imagine we have a multiplexer like this. A lot of things come in. I'm going to give this control bit, let's call it a code. And based on this code, we're going to have this output representing the inputs, right? But it's going to be a long string of data, okay? One after the other, one after the other. Some long string of data coming based on these inputs and based on the code. At the end, you may think about it the same exact way as a demultiplexer. Demultiplexer, demux. This is mux and demux, same exact thing. However, you created this code, you're going to give it to the other guy, and you're going to say, use this code to start bringing out each one of the inputs from a different outputs. So you're going to have multiple outputs, and then you have something you can use. Okay, why? Because if you use a wire for 5 miles, for example, these 5 miles, this wire has a resistance. If it starts with 5 volts here, now here is 0.1 volts, because the resistance will attenuate the voltage and the signal is completely gone. If it was a 1 here, that 1 is now 0 on this side. So wires, they are not helpful. What is helpful is light, meaning fiber optic. We go with fiber optic in one wire. When it gets to the other side, we reconvert it again and things like that. So there is a lot of solutions like this out there, but they always help. And these tools, although they may look like it's trivial, some of them are extremely sophisticated. Okay, further, this is a multiplexer. See, as we said, control line 0, S0 to S1. Determine which of the 8 other input lines D0 are routed to the output. Just like we explained, it's just a different word. This circuit can be used to store information. Circuit as memory. This is how memory looks like. Watch this, it's really cool. An SR latch store a single binary data. Okay, binary bit 0, 1 or 0. There are several ways an SR latch circuit can be designed using various kinds of gates. If you look at this, you're going to see that the X and Y, the information X and Y stays until these two are excited again. It's really cool how memory works. Assume that S and R are never both 0. Okay, the design of the circuit guarantees that two outputs X and Y are always complements of each other. They are the opposites of each other. The value of X at any time is considered to be the current state of the circuits. So let's say we're going to use that. That's the current state. Therefore, if X is 1, the circuit is stored in a 1. X is 0, the circuit is stored in a 0. You can do the math and you can see what the calculation will be like. So if you put a, remember they said never the same time, they never have 0 at the same time. So it's either going to be a 1 0 0 1 or 1 1, right? So if you give S a 1, R a 0, for example, so if you give 1 here, this is a 0, whatever the previous state, you can imagine one of them and you start from there, because that's the question you're going to have, is what is the state of the output? What was the state of the output previous me starting this calculation? You're going to assume one of the states and you're going to see that however you assume it, it's going to lead to the same result. X will stay stored until it gets excited. Integrated circuit, don't get too confused about this, okay? It's a little bit too complicated to do the zeros and ones, but you can try it and create a table, or even go to YouTube and see how this representation, the circuit as a memory, how this representation is explained. I think I did put a video about it in there. Sure. Integrated circuits, a piece of silicon on which multiple gates have been embedded. Simple as that. Integrated circuits again, and this is the kind of multiple types of integrated circuits. And you're going to see what's the difference based on the number of gates. Okay, small scale, medium scale, large scale, very large scale. Okay, very large scale, over 100,000. And we're talking a lot more than that. Chips exist with over 2.6 trillion transistors. Trillion. The number is phenomenal. This is what we call miniaturization. that allowed us to have chips that can do crazy stuff, very, very small. And it's really good too because they don't use too much energy. So our computers don't get too hot because they are not using too much energy. And that's how your battery lasts longer. Everybody's happy, right? So the smaller these chipsets are, the better it is. But again, there will be a time where they can go any smaller. We are expecting it's going to happen. And when it happened, we will switch technology. We will probably go from zeros and ones and go from electricity transmission of information to probably biological transmission of information. There's people working on this, by the way. It's crazy, but it's out there. There's people who are trying to do uh, DNA coding, things like that, trying to include both technologies and create literally computers that functions not with zeros and ones. Integrated circuits. This is integrated circuit. Remember we talked about there is a power and a ground, and in this one it has four gates, and that's exactly how it looks like too. I've seen them. Forgot what they're called. The 7404, 7408. I completely forgot the gates because I played with this for years. So some gates, some circuits, they have more than just four. They may have eight, they have six, depends. But generally, the pins in integrated circuits are in R14. Generally, they can go double, but generally, all the circuits you're gonna find they are 14, 1 to 7. Well, may I ask why? Why 14? A lot of motherboards are built like that. Again, if you're playing with this, you're gonna build your own motherboard too. You're gonna make the holes and everything. You're gonna work if you really want to play with this stuff, which is really, really cool science to do. Because we did build stuff that's from scratch. We built everything from the motherboard to the circuitry to the lines to you name it. And that was very interesting. Ethical issues. So this is basically the end of this chapter. I'll let you go over this stuff. I generally don't talk too much about this because I'm a scientist and history and personalities interests me the least. Let's just say that. Anyway, again, thank you so much for staying with me. I know it was long, but it's one of those that we have to spend a little bit of time because you may not have a chance to talk about this again, okay? Make sure you read the chapters, please. Read the chapters. There may be things that I have not mentioned, but generally, I do go over 95% of the stuff you have following these PowerPoints. Again, if you have any questions, do not hesitate to reach out to me. And I'm easily reachable, so just email me. You have my email, my syllabus, and we'll talk. Okay. Thank you so much. Have a great day.